Yeah, anyway, so thank you for letting me talk. Let me show my work. I am a postdoc at Concoli Observatory, like it was said, and I've been working with these young stellar objects, which is smaller scales than we have been talking about this morning, but I hope you find this interesting. This is one part of the science that I've been working on, and yeah, so let's get to it. Well, recent results have shown, actually from ALMA, have shown that planets are actually being formed in protoplanetary disks younger than what was expected. Due to the masses that we're measuring the disks, we know that younger disks have more mass, therefore that's when the planets have been formed, because later disks do not have enough mass to form them. And therefore, it's interesting to see what is the chemistry on these disks, because it is expected that when a planet is formed, it will inherit the properties of the disk, of its protoplanetary disk, right? And now chemistry is being started to go deeper using ALMA and NOEMA, and in the future, not so far future, JWST. And there are a few large-scale projects. I'm here in the image. I show the results of one of them, which is the ALMA DOT survey. They studied 6 stars in Taurus. They got some nice chemistry images. We can see the whole distribution of extensions depending on the molecules. It's quite interesting. However, these are like smaller molecules, CO, CS, H2CO. Now we are here we are going to be talking about larger molecules, which are complex organic molecules, which are hard to detect in this type of disks because these disks are too cold. As I will show in a few, in the next slide, we need higher temperatures to detect these disks. And for this, we are aiming to use eruptive young stars to detect these molecules. So what is an eruptive young star? Well, part of the star formation process is that we have the cloud, it collapses, and it starts to form the star, the protostar with the disk. And accretion was thought to be constant. Well, not constant, but it was like soft and shallow. And now results have shown that it's actually episodic. We have periods where the accretion rate goes super high, then it goes down, goes up and down, and so on. And these can be changes of up to 4 orders of magnitude. And whenever this happens, we say that the star is erupting, it's an outburst star. And we usually classify this into fjords and exors, depending on the magnitude and the length of the outburst. Here we are only going to be talking about the fjords. Okay, yeah. So the fjords are identified with a sudden typically with a sudden brightening in the optical or the near infrared, and then they last for several decades. They can stay like constant, or they can be slowing down. They, like I said, they typically last long, but there are some of them that turn on, turn off, then on again, and so on. These type of objects typically occur in class 0/1 or maybe class 2 objects, depending on who you ask. What happens is that the accretion rate increases, and then the volumetric luminosity of the whole system goes up. From a few, these are low mass stars, so it's a very few solar luminosities, and it can go up to a few hundred solar luminosities. In one case, it went from like 7 solar luminosities to 300, so it's quite a significant increase. This causes that the volumetric temperature of the disk goes up. Usually before the outburst, they are below 100 Kelvin, which is what causes the molecules to be frozen. And then after the outburst, the temperatures are above 100, and now they sublimate. So this is like the schematic of what I'm talking about. So we have like a normal star here, and then we have dust grains, and the molecules are frozen here because the temperatures are lower. And then the outburst happens, the snow line gets pushed out, and now these suddenly desorbed molecules can now be detected. So this is exactly what we are going to be doing. However, so theoretical results have shown that if we turn on and off the luminosity of the system, we can have different changes in the chemistry, not just caused by the desorption of these molecules, but also by gas state, gas chemistry, right? So now we can have evolution because we have high energies due to the accretion outburst, and now changes can start to happen. So these theoretical models were done at different scales from the envelope. Here you see in the bottom left, it goes up to 1,000 AU. And then we go to scales up to only the protoplanetary disk, which is in the bottom right. But then observations showed up, and then we start to actually see these things that the predictions suggested. And it's important to mention suggested because the theoretical, they can run their code, and then they have pre-outburst, during outburst, and after outburst. But these fjords last for, actually, we don't know how long they last for because we have only seen one finish. So it's expected that they last about 100 years. So maybe our grandkids will have enough information to know more about this. But for now, we have a snapshot of the chemistry during the outburst. And this is what these results have shown. These are from ALMA. These in the top and the bottom left, these are from BAA3 Ori, a famous fjord star. And this is from the bottom right from L1551 IRS 5, which is another fjord-like star. And we see all of these chemical lines detected with ALMA and with NOIMA. So we have our observations here. We ran this project a few years ago, and the whole goal of this science goal of the project was to observe the disks, see what they look like, maybe see the outflows and the envelopes of the gas, and that's it. The goal was not the chemistry. However, we have two spectral continuum windows, and when I was making the cubes, cleaning the images and all this stuff, I found that some pixels were brighter than the others. I made a nice map, and then I found all of these emission lines. I didn't know what they were, so I asked someone that knew more than me, and turns out that they were emission lines from other chemistry molecules. So I got interested into, and I followed this up. Our observation setup included two ALMA configurations because we wanted to have higher angular resolution, and we went to the ACA and then the total power antenna because we wanted to recover all the extended emission that we expected from the envelopes, right? So we published our continuum analysis in this paper. You can check this QR link. For more questions, of course, you can ask me. Then 4 of these targets, of these 10 targets, actually have emission lines. I went through all of them. I only found these 4, and these are the ones that I'm going to be focusing on. Because they are optically thick in the continuum, I decided to move the pixel that I'm going to use as an aperture a little bit further away from the center so that we don't have optically thick lines. These are the results that we got from these systems. I did not show the south disk of the L1551 IRS 5 because it's mostly, there are lines, but they are too weak. So you will mostly see noise. And for the slides, we don't want that. So I identified a few of the molecules that we detected. Very interesting. We got methanol, we got methyl formite, and those are the 2 ones that are more common. And then we also have these other ones here, and we detected C18O, well, 18O methanol in only one of the sources. So this is the one that we're going to be focusing on in a little later. So we took this spectra and then I ran them through gases, assuming that they were optically thin, and we used LTE assumptions. We did some MC fitting so that we get the column density and the excitation temperatures of the system. Then we take the column density and we want to see abundances because we want to see, numbers relative to each other. Usually people try to do this with respect to H2, but as we have seen earlier this morning, the ratio between C and H2 is not so obvious. So it's just easier to do methanol, and then we just keep everything with respect to comms. So com against com. So now we have this here in the left figure, we have the abundances of these different species with respect to methanol for the different fjords that we have here. Here in the left, we have the ones from this work, and here on the right, we have the couple that I showed earlier based on the literature. And just to put these numbers into context, I took this image from this Bianchi et al. 2019 paper, in which they show the abundances for some class 0, class 1s, and some comets, and so on. So we have that our values are aligned with them. However, our values, we know that they are upper limits because we know that methanol is optically thick, since methanol gets optically thick extremely easy. So good luck. As I mentioned, we have 18 methanol detected in one of the disks. So we just assume that the fractionation, the ratio between 16 oxygen and 18 oxygen is the literature, which is 560. We could estimate the optically thin column density of methanol. So then I use that one for this. And now these are the optically thin abundances of methanol. And now we have values that are more aligned to what we see here for the class 1s and the class 0s. So this is kind of the important result for now. The fact that class 1s are really hard to detect. So now we would have, if we update this plot, we would have a nice clump of class 1s here because of all of these sources are class 1s. So yeah, this is what we have for this. And Bianchi et al. 2020 had an upper limit here for methyl formate, which aligns with our estimate of the optically thin abundances. So that's quite nice. So now I'm only going to focus on IRS5 North. So this is the full spectra for IRS5 North. It's a bunch of molecules that we detected. Most of the species are already ID'd. You can see them there. There are a few unidentified lines like this one here, here, or here. They might be, well, actually, we don't know what they might be. That's why they are not identified, right? But we'll see what happens for them. If not, we can just leave the paper as it is. But we found some interesting species that only have one transition in our spectrum. So we cannot do a lot of them. We just kept them here ID'd. We just did some basic analysis for them, H2S, H2CO, DCN, for example. So anyway, so we took this IRS5 North spectrum, and then we calculated the abundances against optically thin methanol, and these are the black points here. We are now going to be comparing this to IRS 16293b, which is one of the two disks that were observed as part of the PILS program of ALMA, which was a large program of ALMA to get like a large, deep chemical survey of this source. It's a class 0 source in raw fucus, I think. I don't know. So they got like 10,000 lines or something like that. And among them, they found the species that we also have. So then I took their numbers and I compared them with us, and we find that they are quite in agreement, actually. Here, the less abundant species, which are maybe just by coincidence, but they are nitrogen species, they kind of match nicely. Whereas the other species are, in our case, they are lower than what they found for IRS 16293b. So these differences, with this difference, we don't know what can cause it. It could be that our molecules are actually optically thick, and then our upper limits then become extremely uncertain. They are upper limits and lower limits at the same time, so who knows? So that's one part of this result here. And then finally, we also did some basic maps of these species. For example, here we show methanol, different transitions of methanol for only 3 of them. If you remember one of the spectra that I showed, HARO5A IRS5 does not really have a significant methanol emission. So these maps just look like noise. Here, I just wanted to show that what we see in these molecules, the contours are the moment 0 of the different lines.
2 minutes.
The colors are the moment 1. Thank you. We can see that they are barely extended, but they are extended enough that we can see the Keplerian rotation. So that's quite interesting. And just please notice the extension, they are much smaller than 1 arc second, right? And then in IRS5, we found some species that were extended. So that's what these look like. These are channel maps for these different species, and we can see, notice the scale. So now we have 10 arc seconds. So this is way, way larger than we have found. So we can see that we have this nice chemistry at different scales. And now I actually going to have to do the combining single dish data with interferometric data. The paper is in progress. So hopefully you will see this soon. And yeah, so I welcome any questions. Thank you.
Thank you so much, Fernando, for excellent talk. It's always fascinating to see all the forests of different lines that you get from ALMA. And the ability to do such complex chemistry. Do we have any questions?
So I think, yeah, there are some questions, but I think this was partially answered by your by the last slides, but I think the last one of this is still valid. So you showed maps of the different molecules and how their morphology is. And does this help comparing either different molecules or different transitions of molecules to constrain how far away or for how long the outburst affects the chemistry?
Those are like two questions in one, but well, the extension of the molecules, of course, helps. Let me show the slides again. So the extension works here. This is like my first time working in chemistry, so I was super excited when I noticed that the transitions with higher EU values were much smaller. Right, so this is interesting. So we can see that actually science works. So that's cool. But yeah, we can get here some information. This extension in methanol, for example, we think that this is well, this is more complex, but we think that this is caused because the jets are breaking out the cloud and they are dragging some of the methanol with it because the source has jets and this is the blue shifted side of the jet. So maybe this is what's going on. I still need to discuss this with more people about that. And about the second part of the question is about, well, whether we can know more about the outbursts based on the chemistry. That is expected from the theoretical models. So depending on the model, here you can see if you have different outbursts, these lines will be going up and down depending on the type of outburst and the conditions that you have. So if you see these changes, then yes, maybe you have another outburst earlier, but it's extremely uncertain. The models are models, so you have to tweak these really carefully. You have to know the initial conditions of the system, and we don't know them for most of these fjords because most of them are not studied until they are going into outbursts. So there are very few observations of them. And then when they go into outbursts, we pointed into outbursts, we pointed telescopes, and now we know stuff, but we didn't know what they looked like before. And actually, this is one of the reasons of our, one of the motivations of our ALMA proposal is that we want to see the outbursts happening and then immediately turn ALMA into it, because we want to see because we expect that the initial chemistry right after the outburst is what was before that. And then we want to at least set the foundation, maybe like a first step for a chemical monitoring that can last decades. So hopefully ALMA still works in 50 years and we can get a nice snapshot of this. We can compare abundances and we see the actual effects of this. One of my goals would be before that I retire is that we can find something that indicates, chemically indicates that there actually was an outburst, but still in baby stages. Okay.
That's really exciting. There is a comment from Alvaro saying that the unidentified lines might be vibrationally excited states of some of the molecules you already identified. Did you look into that?
No, I did not. So yeah, these are, that could be it. I need to know more about that, and I hope the question was written down so I can copy it and research into it.
Yeah, it's in the Slack, so or
Okay,
will be in the Slack for you to.
I'll check it out.
There's also a question if any of the methanol transitions are potentially mazing.
Oh, that's actually another question that is in my to-do list because I am interested in these methanol mazers. Maybe this can point into something, but I'm still not into that step yet. That's probably for after the ALMA deadline.
That would be very exciting. Then you can go for high resolution follow-ups of the mazers.
Yes.
That would be really cool. Nice. So yeah, so far I don't see any other questions. Maybe there will be more on Slack. Let's see later on.
Thank you so much, Fernando, for the excellent talk.